Let me. Okay, can you see my screen?
Yes.
Yes.
Okay, so let me start. So yeah, today I want to solve one example of multiple pipe systems, and the main method that we are going to use, you can use it and apply it for other multiple pipe system problems. So the question is as follows. We have a multiple pipe system that is shown here. Uh, can you see my cursor?
Yes.
Yes.
Okay, so we have a multiple pipe system, and we have a tank A here, and then through some pipes, pipe 1, 2, 3, 4, the water is kind of moved downward. And what we want to do is we want to uh, see what water is discharged from atmosphere at point D is here, and we want to find the flow rate at each pipe based on these kind of characteristics that are given for this problem on the left. We don't account for other losses like minor losses here, and we only account for these losses for friction factors that are given us to here. Otherwise, the problem would have given us the minor losses. And yeah, so here you can see that we have these different points, and then their elevation point E, A, B, C, D. And also the pipe characteristics. We have 4 pipes. They have different lengths and also different diameters. And so again, the question is, we want to find the flow rate and calculate the flow rate in each of these pipes. Okay, so let's start. So the first thing that we do is we calculate the areas of the pipes, and this is important for us, especially for calculating the flow rates. So we use the simple formula of the again a square, a circle. So it's PD square over 4, and you have the diameter of different pipes here that are written, and so you can simply calculate the area of A1, A2, A3, and A4, and then A2 and A4, they equal to each other because the diameter is both 6 inches for both of them. Okay, so this is the first thing. It's easy. And then we use this kind of theory that we had for parallel pipes 2 and 3. So if you remember from the lectures, we had 2 relations for parallel pipes. One was the head loss. So the head loss between point B and C should equal, even if you go from pipe 2 or pipe 3. So that means the HL2, which is the head loss at point 2, should equal to the head loss at for pipe 3. Okay, so this is the first thing that we know from the parallel pipe theory. And then the second thing is that the total flow rate is kind of the mass continuity. The total flow rate at Q1 should equal to the sum of flow rate at Q2 and Q3, right? So the flow that comes down and it branches to 2 pipes, the total flow rate of that should equal to Q2 plus Q3. This is kind of a mass conservation or continuity. And then this flow that comes here, and then they merge to pipe 4, it should also equal, the sum of these 2 flow rates should also equal to Q4. So that is what I've written here. Q1 equals to Q2 plus Q3 equals to Q4. Okay. So any questions so far before we move forward? Okay. So now we want to solve and find the head losses between different points. So the first one that I want to find is the head loss between point B and C, which is again equals to HL2 equals to HL3 based on this theory that we said. So we just use this formula that we had for calculating major losses. So it's going to be F times L over D V square over 2G. And F is given here, the friction factor for pipe 2 is given as 0.025. And then the length of the pipe 2 is also given as 800 foot. So we just substitute that here. And D2 is the diameter of pipe 2, which is 6 inch, which would be half foot. So we just put it here. And then we only don't have V, so I just leave it there, V2 square. We don't know what it is. If we knew it, then we would have known the flow rate. So actually we want to find this V2 over 2G, and then this equals to the HL3, which we have written here. And so I just rewrite it here. So F3 times L3 over D3. So F3, based on this table, we can find is 0.045 for pipe 3, the friction factor, times the length of pipe 3, which is 900 foot, over the diameter of pipe 3, which is 4 inch, which would be 0.33 foot, times V3 square over 2G. So this gives us a relation between V2 and V3. So 2G cancels from both sides of the equation. And then if you rearrange all these terms, all these numbers, this is what we get from writing this equation, from this equality. V2 equals to 1.74 V3. So it means that the flow speed at pipe 2 is greater than pipe 3, and it's 1.74 times greater than pipe 3. Okay, so this is the first thing that we get. And then we can write a corresponding relationship between the flow rates between Q2 and Q3. Similarly, so V2, as you know, is, we can write it as Q2 over A2. So Q, the flow rate, is just V times A, right? So I can just write it down as this: Q2 over A2 equals to 1.74 Q3 over A3. And so this gives me a relation between Q2 and Q3. So Q2 equals to 1.74 A2 over A3 Q3 equals to, and then we just substitute the A2s that we had calculated before. So we had already calculated the areas of different pipes here. So this is A2, 0.196 foot square, and A3 is 0.873 foot square. So I just substitute those here and multiply it by Q3. This is going to give me a relation for Q2 and Q3. So Q2 is going to be 3.92 times Q3. Okay. And then we have now these Q2 and Q3 based on just one of them. We have a relation between them. So I just want to use this formula uh, for the parallel pipes. So Q1 equals to Q2 plus Q3. So again, I get a relation between Q1 and Q3. So instead of Q2, I'm going to write this relation that I found here is 3.92 Q3. And then plus Q3, this is going to give me 4.92 Q3. Okay. And so I just write the definition of Q, the flow rate, which is AV. So it's going to be A1V1 equals to 4.92 times A3V3. And then based on this, we can find again a relation between V1 and V3. So V1 equals to 4, I just write this down again. So V1 equals to 4.92 times A3 over A1 times V3. And again, I already had calculated the area, so I just substitute them here. 4.92 times the area, ratio of the areas times V3 equals to 1.23 V3. So again, we found a relation between V1 and V3. And so I can, now I want to find also the relation between V4 and V3. So we know from this relation, Q1 equals Q2 plus Q3 equals to Q4. So I use that relation. And you know that Q2 plus Q3 equals to 4.92 Q3. So I just use that. So 4.92 Q3 equals to Q4, right? So this is a relation again for the multiple pipe systems. And so I use this to also get a relation between V4 and V3. So instead of Q3, I just write V3 A3, and instead of Q4, I write V4 A4. And so this is going to give me a relation for V4 and V3. V4 equals to 4.92 times the ratio of the areas, A3 over A4 times V3. And if you calculate that, we are going to get 2.19 V3. So V4 equals to 2.19 V3. So now we have calculated all the velocities and we have all of them in terms of V3, right? We have V4 in terms of V3, we have V1 in terms of V3, and we have V2 in terms of V3, which is shown here, okay? So now that I have only one velocity that is unknown here, I just write the energy equation between point E, B, C, and D. Okay, so I just go from here to here, or you can go from pipe 2, but I go from pipe 3 because I have calculated everything based on the velocity of pipe 3, so that will make my calculations easier. So just note that the pressure at E and pressure at D is equals to the atmospheric pressure. So in terms of gauge pressure, that's gonna be 0. So I can just neglect the pressure at point E and point D. So this is gonna give me this equation here. So PE over gamma plus the elevation ZE here plus V square over 2G here, but we know it's a tank, so the velocities can be neglected. And also here, there was something here that um, the change in the velocity head is negligible compared to the change in the head between any 2 points of interest. So the velocity heads can be ignored in an energy analysis. So this means that I can just neglect velocity heads because they are kind of much smaller than the change in the elevations. So based on that, I just write this plus ZE, which is the elevation here, equals to PD over gamma plus ZD, the elevation here, and then plus all the losses that occurred here. So HL1 plus HL3 plus HL4, right? So the energy here, we had the energy here, and then this equals to the energy here plus the losses that occurred in these pipes. So that is what actually shown here. So because PE and PD equal to the atmospheric pressure, and in terms of gauge pressure, they are 0, so we can just cancel them. They are both 0 here. And so then we have a relation between different HLs. ZE, the elevation at E, we have it here. It is 150 foot, so I just write it here, equals to ZD, which is the elevation at point D, which is 30 foot, shown here in the table. And then plus F1, the head losses at the major head losses at each pipe. And the problem said we don't need to account for any minor head losses or other losses. So only we account for the major losses, F1 times L1 over D1 times uh, V1 square over 2 times 2 over 2G, and V1 we know it is 1.23 times V3. So I just have it here, 1.23 times V3. So you have it here. So I just substitute it in terms of V3. So I write all the velocities in terms of V3. So we can find V3 from this equation. And then we have the same term for pipe 3 and for pipe 4. So instead of V4, I just write 2.19 V3, which I found here. And so 150 minus 30 is going to be 120 foot here. And then I just write all these. I have all these friction factors in this table, and also the length of the pipes, and also the diameter of the pipe. So I just substitute all of them here from this table. And the only unknown here is V3. So I just write everything in terms of V3. And then finally, based on this equation, simply you can find that V3 square equals to 22.9 foot square over second square. And so we finally found V3, which is going to be a square root of this, and it will be 4.79 foot over second. Okay. So now that we have found V3, the next steps are easy. We just substitute V3 in all these relations we found for velocities to find the velocities of each pipe. So V1 is 1.23 V3, so it's going to be 5.9 foot per second. V2 is 1.74 V3, will be 8.35 foot per second. And V4 is 2.19 V3, so it will be 10.5 foot per second. And now that we have all the velocities, we can simply find the flow rates by this formula, A times V. We have already calculated the areas at the beginning of the problem. So we just substitute those values, and A, for example, Q1 equals to A1 V1, and we get like 2.06 foot cube per second. Similarly for Q2, Q3, and Q4, we repeat the same procedure to get the flow rates at each pipe. Okay, so this is how we can solve these kind of problems. It's a general way of doing that, and we actually found the flow rates at each pipe by using this. So any question?
You had mentioned in class at one point that we have to start by making an assumption for the flow. And obviously you assumed that things are flowing from the reservoir down to D. So you've assumed that things are flowing from E to D.
Yes.
But without having flow signals, we don't know for a fact that it's flowing from B to C in both 2 and 3, right? So aren't we supposed to go back and check continuity or something like that? Or is that a different type of problem?
That was when you have like multiple reservoir. When you have multiple reservoirs, because you don't know, for example, if I have another reservoir here, and then it also kind of has a connection, a pipe connection to this pipe system, then I don't know whether the flow is going to come into from that reservoir into the pipe, or it's going to go out of sorry. So it's going to either go so if I, for example, have another reservoir here, say, let me show it. And then, for example, it is connected via a pipe to this system. So I don't know whether, let's say.
Sorry, I didn't mean to make you do all this.
Yeah, I mean, I just want to, I am recording, so I want other students to understand. Yeah, so if I have this reservoir, and then I don't know, like if the flow is coming here, whether the flow is gonna come from this side or it's going to go into the reservoir, it's going to come out of the reservoir, right? So for those, you need to first make an assumption. For example, say I assume that it's going to come down, like it's going to go out of the reservoir. And then based on that direction, I will solve all these and write all of these and see whether that is gonna kind of satisfy all my governing equations like continuity, energy, and all of that. And if I see that in one of them it doesn't satisfy, so then my assumption was wrong, and so the flow rate, the direction was in the other direction. Okay, but in this kind of problems that you only have one reservoir, then I think it's kind of easy. Based on the elevation, you can have a good guess that it's going to go down, right? And so you don't need, it's not that much complicated.
Okay, thank you.
Sure.
I had a